Let's now use Python to discover the central limit theorem and see if what Carly's just showed us about the theorem actually holds true in a simulation. A quick reminder, the central limit theorem informs us the more times we sample from any distribution, so that can be a crazy left-leaning, right-leaning, even a normal distribution, the sum or average of these samples will tend towards a normal distribution. So to discover this property, we need to sample from a distribution and then aggregating those samples by summing them together. So we're going to do that in those two steps. So let's tackle each of these parts completely independently. The first part is let's sample from the distribution. So a distribution is all the possible outcomes of a particular probability. So what's the frequency of all those outcomes? One sample distribution is the game of roulette. So that's one of your favorite distributions.
Yep, we've seen this before.
And the outcomes of this distribution, we're going to look at winning being red. So this is the color that you usually bet on, Carly.
Yes.
And so the frequency of getting a red outcome is?
There are 18 red slots on the roulette wheel and 38 total. And then the frequency of not getting red is just the rest of them, the other 20 slots, the black and green.
So the frequency is 18 out of 38 of getting red, and the not red is 20 out of 38. And I'm going to do this problem slightly differently than you,
Okay.
just so I can model it as a Bernoulli distribution.
Got it.
So I'm going to say the value of red is success, and not red is failure. So this is basically the number of times my bet wins.
Exactly.
So
rather than how many dollars you actually win.
Exactly. So this will be a little bit more work to convert it to dollars at the end, but this is calculating the exact same problem. So I'm doing this because I can model this as a normal distribution. So this distribution has only two results, so it's a Bernoulli distribution with a probability of 18 out of 38. So we can use Python to sample from this distribution. So to sample from this distribution, we first need to import the distribution. So from scipy.stats, I'm going to import Bernoulli. And then I'm going to create a new distribution. D is equal to a Bernoulli with P is equal to 18 out of 38. So this samples from a Bernoulli distribution with 18 out of 38. And I actually want to take a sample from this distribution. So to sample from it, I'm going to do d dot random value sample, d.rvs.
And I get a 0.
You get a 0.
Losing.
You got not red.
Yeah.
So every time Carly runs this code, we can sample from this distribution. So we could have used this for any number of different things. So we could have also simulated the distribution of drawing for a queen, for example. So here is a bit of code to simulate using a random variable to draw from a queen. So we were able to sample from a distribution, and you got a 0.
Yep, I got a 0.
Awesome. So now we know how to sample from the distribution. Now let's go ahead and actually run this for many, many samples and control the number of samples. So for the second part, we want to discover the central limit. Now we want to simulate sampling a variety of number of times. So what I'm going to do is I'm going to write the simulation that runs 10,000 times. It samples the roulette running in wheel red distribution by sampling only one time each simulation. So what I'm going to do is I'm going to write a simulation. So I'm going to do data is equal to an empty array, and then say for I in range 10,000 to simulate 10,000 runs of this, because as we simulate, we want to do more and more simulations. And this is where the law of large numbers comes in. The more simulations, the better our result's going to be. Mm-hmm. And then I'm going to go ahead and take a sample. I'm just going to say this sample is S, and I'm going to sample from that Bernoulli distribution. And I'm going to say S is equal to d dot RVS, and I'm going to put in parentheses 1. So I'm just going to get one sample, and then I'm going to do dot sum, because I'm going to ask Python to give me the sum of all of those samples. So the S is going to be the sum of all of the samples when I do X number of samples. Here, the number of samples I'm going to do is 1.
Sounds good.
And then I'm going to accumulate this variable. So D is equal to curly brace S colon S, data.append, open parentheses D. And then I'm going to go ahead and create a data frame, df is equal to pd dot data frame of my data. So what this is going to do is this is going to run 10,000 samples of my roulette game using my distribution D, getting one random sample each time. So I'm basically simulating just having one sample. So this is not a very good result according to the central limit theorem because I'm only taking one sample. So I don't expect this to be normal.
So I went ahead and I imported pandas as PD and then created my data frame. And I have one variable S, 10,000 rows, and they are a bunch of ones and zeros.
Awesome. So let's create a histogram out of this. So let's do df.plot.hist and see what this histogram looks like when we're just sampling one time.
Ooh, so this histogram, interesting. It has two bars, one at 0 and one at 1. And the one at 0 is slightly taller than the one at 1.
So I've got two bars, 0 and 1. And the one at 0 is slightly taller than the one at 1, which means we fail more often than we succeed. And that makes sense. But is this a normal distribution?
Not at all.
So the central limit theorem says we will actually get a better result the more samples we take. So I'm going to say, I'm going to modify this value so that I can find, use k samples, which is something we like to say as a mathematician or a statistician or a computer scientist. And k is going to be the number of times that we run the number of random value samples we pull from our distribution.
Sounds good. So what's our first one?
So I think we should modify this code and actually put k in here. So why don't we go to that d.rvs and delete the 1 and put k in there. And at the very top above data, let's say k is equal to 10 initially. So we're replacing 1 with k, and we're putting k equals 10 at the top.
Got it.
And now if we run this, we should see that we're taking 10 samples. And if we check out what's in the data frame, what do you see that's in the data frame?
I actually see S now has different values. It has 6, 4, 6, 7, 5, 8, 2, 1, 5, 5.
Because what we're doing is we're summing the total number of times we won roulette. So here, sometimes we won 6 times, sometimes we won 8 times. I hope I was playing that day.
Right.
So out of 10 runs, we are seeing how many times we won out of those 10 runs at the game.
Got it.
So let's go ahead and make a histogram with that k equals 10.
Sounds good. And my histogram, when I go ahead and run that code, wow, looks almost like the normal curve.
Oh, so we're getting a lot more normal. We have kind of 2 peaks in the middle, and then it kind of spreads out from there. So it's looking much more normal. But what the central limit theorem says, it's going to become more and more normal as k increases. So let's go to 100.
K equals 100. And now my histogram looks even more normal.
Looking even more normal. And let's go crazy and let's go to 10,000.
All right, 10,000. So our K is now going to be 10,000. And we should see that our histogram is very close to the normal curve at this point. And when we do that, it definitely is.
So it's looking more normal, more and more normal. But what I think I want to see is I want to see more detail here.
Yeah.
So we're only by default getting somewhere between 8 to 10 bins in Python. So if you say bins equals 100, we're going to get 100 individual bins in this graph.
There we go.
And this looks like almost a perfect normal curve. And as we sample more and more times, this normal curve is going to look more and more perfect. Because the central limit theorem really tells us as we grow from k equals 1 to k equals 10,000, it's going to look more and more normal. And just as a reminder, let's go back to k equals 5 after seeing this beautiful curve.
Ooh, yeah.
Is this just working because we changed the code? Or if k equals 5, this should look like a terrible normal curve. And with 100 bins, it's going to be very interesting to see.
Ooh, yeah. There's spaces, a bunch of spaces.
Lots of spaces, not nearly as normal curve looking. And you can definitely see, and I feel like this really discovers the fact that the central limit theorem really works.
Discovering it in Python.
I love it.